So today I'm going to be talking about the effects of stellar multiplicity on disk dynamics and planet formation. So I will try to give an overview what's been happening in this field and what we've done with Phantom and mcfost on this specific topic. I will try to mention many works. I won't go into deep detail, but if you have questions, we can talk during the week. So I'm working in Grenoble. And this is part of an ERC project that is ongoing and currently happening there, focused on stellar multiplicity and planet formation. So this is the outline of today's talk. First, I will motivate why multiplicity connects stars, disks, and then planets. Then I will talk about disk dynamics in multiple stellar systems, a bit of theory and some observations that we have, and the modeling we've been doing in this particular field. And then, towards the end, I will try to touch on the missing link between disks and exoplanets, and with a specific emphasis on multiple stellar systems again, before reaching some open questions and conclusions. So the first part. So this is something that everybody knows. We have this kind of giant molecular clouds where we know that young stars form. And we have this idea that from the collapse of a very big cloud, we have a disk which is formed. So this is just an example of a stellar nursery. And this is the classical view we have for star formation. So you have the cloud, it starts falling onto an overdensity, and then because of the conservation of angular momentum, you end up with a disk. And we know that this disk is mainly done gas, and there is a bit, 1% or more of dust. And then we know that eventually this will form a planetary architecture around the star. But you should note that for simplicity, it is often assumed that this occurs in isolation and there is only one star. And this is far from being true, and that's what I will try to motivate in the next part of the talk. But we can see that star and planet formation are very strongly connected. All right. Then one can look at these stellar nurseries and try to count what's the fraction, or try to estimate what's the fraction of multiple stellar systems. So that's basically this quantity here, which you take all the stars and you remove the fraction of the stars which belong to multiple, or to single stars. So this F1. And you end up with this ratio, which can be approximated by the fraction of binaries plus the fraction of tertiaries, quadruples, divided by the entire number of stars. And then you get this kind of trend. So here you have the multiplicity frequency, and here you have the age of the region you're observing. So this is like a sketch of the observed trend. So you see that when the stars are very young, so we call them class 0, the multiplicity fraction is really high. It's between 40 and 70%. Then, as time moves forward, we see that class 1 and class 2 have a smaller multiplicity fraction. But the thing that you should notice, so here for completeness, I put some ALMA large programs that have been targeting these regions, and some very nice telescopes that are providing data for main sequence stars. I will talk about this at the end. And we see, so when disks form, is basically here, at the very young stage of the stars. And you see that multiplicity seems to be the norm rather than the exception. So this is very important. When disks form, it tends to happen around multiple stellar systems. All right. So then there is this very famous simulation done by Matthew Bate a few years ago at the University of Exeter. So here, what he's simulating is basically the collapse of a very big cloud, and you see how stars form in that cloud. And what he's plotting here is what happens as soon as you form a star, you start plotting what happens around that star. And you can see from this movie that stars tend to encounter each other. We have a very broad variety of multiple stellar systems where you have accretion from the environment. You have very misaligned architectures that form very early on. Stars encounter each other, exchange material. So we've heard about this before in Ellie's talk. And this has been an active field of research, but what's emerging from this is that multiplicity needs to be taken into account when it comes to disk dynamics. And there is an enormous diversity of disks that should be considered. So here I'm just showing two examples of very young stars with material surround them. So here you have the case of this phone number, L1448 IRS3b, where you have very young stars, and then you see that there are accretion flows, and there is material around which shows substructure. Again, here we have the cosmic pretzel, where you have two stars, and then you can see these spirals, and you can guess that they're very likely misaligned with respect to each other. So what we're actually seeing here is that we're seeing multiple stellar systems in the act of forming these disks that we're interested in. And again, this does not occur in isolation.
Can I just ask, what does it start with on the right-hand side? 2 stars?
You have 2 stars here. This,
and a disk?
And the disk is starting to form around.
So you form, no, you don't form a disk, or you do have a disk?
So this is kind of a disk. It's not yet like a complete disk, a full disk, but this is a circumbinary disk. And there are some hints that there is material around each of the stars as circumstellar disks.
Ah.
So I will talk about the kind of disk we can have in these systems. So there is this very nice idea that now is more than 50 years old, is that perhaps all stars are born as binaries or multiples. So this was proposed by Richard Larson. And something which follows from this idea is that most, if not all, single stars today were once part of multiple stellar systems, right? So I really like this idea because that's what I'm working on. But let's see if we agree on these 3 facts. So we have the first fact is that young stars tend to be part of multiple stellar systems. I showed you why. The second one is that young stars, let's say of the order of 1 million years or perhaps less than that, have protoplanetary disks around. And the third fact is that protoplanetary disks efficiently form planets. So if we all agree, does anybody disagree with this? Nobody. Okay. So I'll assume everybody agrees with this. Okay.
If we said no, what would you do?
And we can chat. We can chat. But for sure, I mean, I guess everybody in this room agrees with these 3 facts, right? I'm interested if not.
I wouldn't say they all have protoplanetary disks.
All right. So some of them, a good fraction of them, would that be okay? Not young, I mean, depends on the mass.
I would say there's plenty of class 3 sources that are less than a mega year old.
Class 3, okay. All right, so you're the only one who disagrees a little bit. Okay, assuming everybody but Daniel is okay. The unavoidable conclusion of this is that planet formation is deeply impacted by stellar multiplicity because it modifies the initial conditions that you have at the onset of the disk formation and the subsequent disk evolution. And in the talk, I will combine some hydrodynamical simulations we've been doing on this and some recent telescope observations that there are on these sources. Okay, so before we start, we need to understand how the number of stars determine the number of possible disks. So it's a very simple sketch. If you only have 1 star, you have 1 disk around. That's easy. If you have 2 stars, you can have up to 3 disks because you have 2 circumstellar disks, possible circumstellar disks, and 1 circumbinary disk. And when you go to 3 stars, things get a bit more complicated. You can have up to 5 disks if this is in hierarchical configuration, which means basically that the distance between these 2 inner stars, so we call this the inner binary, is much shorter or smaller than the large distance between here, between the inner binary and the outer companion, right? So we see that based on the number of stars, you might have different arrangements. And we will try to see how do disks evolve in multiple stellar systems.
In the one on the right, you have 2 stars close together and the other one apart.
Yes.
Do you ever have 3 close together?
That can happen at the very beginning because we think that at the onset in this molecular cloud, you have this kind of random encounters. And at the beginning, you might have 3 stars that are relatively close to each other. And then at some point, that will decay towards a more stable configuration.
3-star systems break up if they're close together?
Yes, they will tend to go towards hierarchical configurations, which are much more stable. And that happens fairly quick. But there is a transition in between both. But that's what we expect to find, actually, more often. So to understand how the inner binary impacts the disk, we can use an analogy. I really like this drawing by Dali, where you can see that you have 2 dancers moving around, spinning around, and then you have this dress of the dancer here, which goes around. That shows some signs of eccentricity. So you can see here like eccentric orbits. That's the kind of things that the binary will do on the disk. And then you see that each dancer is also spinning a little bit around its own axis. So that's what you have here. That would be the circumstellar disk that we have. So the idea here is that the binary is as the source of asymmetry, and that leaves very characteristic features. And here is when SPH is very robust to model this kind of problems, because as Daniel was saying, we do not rely on a grid which will a bit determine the kind of systems that we can model with them. SPH is totally free of these kind of boundary conditions. And it's very good because we can deal with non-coplanar geometries and accretion and do many, many things that are very hard to do with grids. So that's why I think that SPH has allowed us to work on these systems very efficiently. And another image which I think is very good is the egg beater image. So here you can see the binary. So this is the binary, and it's messing around with the disk. So this is something that has been studied. So this kind of phenomena with the disk and the binary as an egg beater has been studied in the 90s. So there is this seminal work by Artimovitz and Lubov, where they basically put, so these were amongst the very first SPH simulations done with circumbinary disks. So they were putting two stars in the center and then see how the gravitational perturbation of the stars would impact the surrounding disk. So this is a circumbinary disk. And the main question here was try to understand what kind of structure I can form, what's the size of this cavity. Here, initially everything was coplanar. Then with time, things went non-coplanar. And also, there is some very recent work by Kiran Hirsch and collaborators using phantom here, where you can see that this is a very degenerate problem, in the sense that you have many parameters that you need to take into account. So one of the most important ones is the mass ratio. So you take the less massive star and you divide it by the mass of the more massive star, so the secondary and the primary. Then you have the semi-major axis, which is basically the separation of the binary. Then you have the eccentricity and the mutual misalignment between the binary orbital plane and the disk orbital plane. Okay? So this would be theta. And here you see an example of what happens when you increase the mass ratio, so from a light companion, light stellar companion, towards an equal mass companion. So both stars have the same mass. And you can increase the eccentricity. And you see that the shape of the cavity changes, but also the overdensities that you might form and the kind of spirals that you get in these systems. And this is, again, a very active topic of research. But essentially, what you need to remember is that we can connect the cavity structure and the morphology with the binary parameters. All right? And here is where everything began for me. Was working with Daniel. So this is a work we did together where there is this fascinating system, HD142527. So this is the first time I was modeling a binary together with Daniel. And this was an amazing system because there were multi-wavelength observations of this system. And we knew that here you have like two shadows here. There are some spirals over there. There is a big cavity. And actually, it was proposed by Fukagawa many years ago, almost 20 years ago, that perhaps there was an inner companion in there messing around. And that stellar companion was later found and started to be characterized. So this is what you see if we zoom in inside. This is what you see. So you have the primary, and you have a companion detected here. And you only know the position of the companion for a very short arc. And you can try to guess what's the full orbit of this companion. So to do that, you need to do some Monte Carlo simulations, try to guess what are the orbits. But basically, a long story short, you have two kinds of families, the red family orbits and the blue family orbits. And the question we're trying to address here is, can we tell something about which type of orbit it is? So we tried many things. And the one that worked best in the end was this one here, where we have a misaligned eccentric inner binary, which is periodically perturbing the disk. So it's naturally forming a cavity. But then you see that there are some spirals on the right. We have a misaligned circumstellar disk that formed from the material coming from the circumbinary disk. So this will naturally also cast a shadow. So this model was really good and robust. And as Daniel was saying before, this was then interfaced with mcfost in order to create synthetic observations and do a one-to-one comparison. And I think this work was perhaps one of the first ones that did that very robustly. And then some works followed after that one. So I would like to talk about this system, HD143006. So this is a work led by Giulia Balabio and people here in the room. So the idea here is that this is what you see when you observe the disk and you just hide the star with a coronagraph. So you see that we're not seeing the central star, but we're seeing the very tiny dust particles that are, so this is a scatter light image. So you're seeing like the emission from very tiny dust particles. And you see this very enigmatic image here, where there is like a big shadow on this side. There is this overdensity here. And what the observers proposed initially is that there is a disk breaking mechanism happening in here, in the very inner parts, which breaks the inner part of the circumbinary disk, which then casts a shadow. The problem with that is that in order to make that work, you need an equal mass binary. That's what the theory says. But observationally, they know that the mass ratio needs to be below 0.2, which means a light stellar companion. So that's the idea that Julia explored. She considered different scenarios for this. So we have the binary, so this is a face-on view of the system. These are phantom simulations again. You're seeing the density. So you see face-on view, edge-on view for 3 different models. So here on the left, we have the binary-only model. Here we have a single star plus a planet. And here we have a binary in the inner part, which is misaligned with respect to the disk by 60 degrees, and a planet in the outer parts. And what's interesting here is that, well, things are very different in between the models, but the one that worked best was this one, because we were able to break the inner part of the disk, and then the outer companion here will clear the cavity, and this will give a very good result when we compare with the observations. And again, here I'm showing a phantom and then a mcfost post-processing, and this is the kind of image you get. So you see that we recover this shadow that we were initially interested in. There is some overdensity here, which moves a little bit around, so it can also be found more or less over here. And the interesting thing here is that we are proposing that this, which was considered a single star, it's perhaps a binary, and perhaps there is also a planet in there. We asked for time. Unfortunately, we didn't get it to confirm this, but perhaps it will be found in the near future. But you see that as soon as you put a binary, everything becomes very interesting and you have a lot of structure that naturally emerges from this. Another very nice, interesting, so here I was talking about circumbinary, if you wish. So 2 stars in the center and what happens to the surrounding. But if we now go to a circumstellar disk in a binary, so you have a binary moving around, and then you put a disk around one of those. There is a beautiful laboratory called HD 10453, where this is the disk that was observed. Again, scatter light, so very tiny dust particles re-emitting the light of the star. You hide the star here, and we know that there is a companion here, over here, right? And you see that there are some spirals. But again, we have no clue of what's the orbit of the outer companion. So we can do something similar to what was done in HD 142527. We have a very small arc here, and when we can draw all the possible orbits. And you see that there is a big spread on the face-on view, but also on the edge-on view. And this is what actually Jean-François González did with Phantom. So again, very nice application of what Phantom can do in binaries. You see that we consider different orbits. So I'm just showing 4 here, but we did this for at least 8 orbits, I think. And you see that the outcome is really different. And one interesting thing here is that since things are misaligned, this circumstellar disk will start precessing. And so we need to catch that at the right moment to see if it works or not. But it also changes its inclination. And our best case, the best orbit we found, is this one here. And for that, we pushed a little bit further the modeling. So we took this, our best orbit from this work, and then together with Beck, who is in the room, we did a second work on this to try to understand what's the origin of the inner cavity, what's carving that inner cavity. And actually, we can say, we can put an upper limit on the mass of the planetary mass of the body that's there. And the interesting thing here that we were not expecting initially, but then it was super cool to work on this, is that we have a phenomenon that we call the sort of Precession-inception in binaries. Because here, the thing that the outer companion, so here is a sketch of the system. So you have the observed disk here. You have the outer companion, which is in a misaligned orbit, which is driving the spirals. Then you have an inner companion here. And the interesting thing here is that the outer companion will make the outer disk precess, but also the inner companion will precess with it. And the thing is that since the inner companion is specifically there with the right mass, it will disconnect the angular momentum transport between the outer disk and putative inner disk in the inner parts. And that guy here will precess and will be driven by the inner companion. So you have this kind of precession inside precession. So that's why we call it like this. And again, this is something that naturally happens in multiple stellar systems, in a binary. And now, recently, we moved now to triple stellar systems, because the more the merrier. We have fun putting more stars in there. So this started basically when we started working with Simone Ceppi in the end of the back of the room, and he did the implementation in Phantom to have hierarchical configuration of triples. I will talk about his work later. But this is an ongoing work we're doing with a PhD student in Grenoble, Antoine Alaguero, where we basically have this system. Again, we're choosing a laboratory that will give us good information and something to play with. So this is V892 Tauri, which is a binary. So you have a binary here with a circumbinary disk. So here you can see the sketch. And there is an outer companion. But again, we have only one position. And in that work, where they first detected the circumbinary disk, they proposed that perhaps this is a triple stellar system where we have interaction between the outer body and the circumbinary disk. So this is what we model with Phantom. We have an inner binary here, and here we have an outer companion, which is in agreement with what we know from observations. And you see that the periodic perturbation of this guy triggers some spirals here. But most importantly, the fact that this outer companion is misaligned with respect to the circumbinary inner plane makes that you naturally drive a warp, a misalignment of the circumbinary disk. And this is something that was proposed or that observed at the edge of what you can observe in Long's paper. And so here we see that misalignment is required, because if you put everything coplanar, you don't drive that warp. So we can firmly say that this is very likely misaligned. And we're working on this. And ideally, we would like to have some more kinematics and again, interface this with mcfost. But it's interesting because here we have this disk which is being carved from inside and from outside. All right, now the work that we did with Simone and other collaborators is to see if it makes a difference to be in a binary or in a triple stellar system. So here what we're doing is that we're comparing what happens when it comes to accretion, when stars accrete material. So again, here we're relying on this simplistic picture where we have zinc particles that accrete material as soon as they cross that boundary. So you have a binary here that is to be compared with this version of triple stellar system where you have that the secondary is split. So the secondary is the less massive of the two binaries, of the two stars, is split into two stars. So we have one star here and two stars here. Or this version here where we split the primary star, so the more massive companion. All right, so this is what Simone did. He ran a large bunch of simulations, and we were trying to see if we could spot any differences in here. So this is it's a bit tricky to explain, but I will try to be clear if I can. So correct me, Simone, if I say something wrong, but basically you have this parameter lambda here, which is the ratio between the accretion happening onto the secondary and the accretion happening onto the primary, accretion rates. And here you have the semi-major axis, the wide, Q-wide, it's basically how wide you put your inner, so you have your outer companion and your inner companion is how wide this separation is. And you see that in green is our fitting for what we did in this work. But we can see that based on how you split actually your inner binary, if you split, for example, the secondary, you will have a higher lambda. So in this case, msec is considered as the sum of the accretion rates of the inner binary. And you see that we can have some deviations, which are important. But also in this case, we can also play between the ratio of the semi-major axis of the small binary with the wide binary. So again, here we're changing a little bit how they are in space. And then here, what you're looking is that at the secondary, how the secondary in a triple version accretes over how the binary accretes, the secondary in a binary accretes. And you see that there are some deviations. And I think Simone can talk to you about more if you're interested in these kind of trends. And another thing we've been working on triples that I don't have time to explain is precession and polar alignment in multiples. So how some disks that are, so you have this disk gearing effect, but then you can have disks aligning polarly, so orthogonally to the binary plane. And there is an ongoing work on this, and this is an active topic of research. All right, so now I will touch very briefly on flybys. Eli already talked to you about flybys. It's what happens when you have two stars encountering. So this guy is on a parabolic orbit, so we'll encounter this disk only once. So this is what you see from a face-on view, but you can look at this from an edge-on view again, and then you see that the fact that it's non-coplanar leads to this kind of spirals and bridges in between the stars. And this is a work we did together with Giovanni Di Piero, and other collaborators here in the room, but we basically modeled all the dust species. So here we run single simulations each time. Now, as Daniel was saying, we can do this just with one simulation, which I think is great because this was very time consuming and a very long project. But essentially, all right, what you can see here is that based on the size of the dust that you will have different structures emerging. So I will just show two examples. First, a prograde encounter and then a retrograde one. So you have 1 micron particles and 10 centimeters, and you increase the size. And this is important because it depends on the coupling, the degree of coupling that you have between dust particles and gas, and that depends on the size. So this is for prograde. You see that here, dust is much more concentrated. And then you will see that for retrograde, things are completely different. So I have 10 or 5, all right. So I will go a bit faster now. So this is what happens for retrograde. Everything is much smoother and the structure is less dramatic. But the good thing is that you can connect this, what we did, this modeling part with observations again through mcfost. So mcfost here is key to connect these hydrodynamical simulations with different observables that we can have. So here you have scatter light, here you have ALMA moment 1, which gives you basically an idea of the kinematics, and ALMA moment 0, which gives you an idea of the distribution of the gas. And the analogy here is that we can see these things as flybys, as crime scenes. And what we want to do is to catch the perturber red-handed while it's perturbing the disk. So we have some gallery of flyby suspects. So this is from a recent review we wrote with Daniel and Francois Menard, where you have different systems. And you see that there are 2 stars interacting with each other. Eli talked about this guy here. I'm going to briefly mention the case of UX Tauri, where you have 4 stars in the field. So a binary there, single star here, and another star here. And if you push the observations to the limit, this is the kind of things that you see. You see that, so we are zooming here around these 2 stars. And what you see is that there is a disk here, and you have another disk here, and there is some spirals connecting both of the stars. And this is very well in line with what we did for flybys, and we did a simulation on the right that matches almost perfectly what happens here. There is a discrepancy here we can talk about later if you want. But there is this idea that there are second-generation protoplanetary disks, and there are many works on this, recent works by Eli and also Jeremy Smallwood. We also have kinematics, but now going towards the last part of the talk, let's see what are the implications for planet formation actually, trying to draw some conclusions here. So this is what we can see, class 0 or 1 and class 2. So you see that there are very fascinating structures, but is this a problem or a solution for planet formation? So actually on the problem side, we see that disks are truncated, so we have smaller disks. We also have less material available to form planets, so we should expect to form less massive planets. Some people think that there are also very short-lived disks because you can perturb them and then you have some chaotic motion of these disks. There is also a faster radial drift of solids because you have a steeper disk in the surface profile. So that makes that solids will move very fast towards the inner regions. And also the fact that you are exciting the movement of particles having eccentric orbits, and that leads to destructive collisions. So this is something, it's an unsolved issue, I think, to understand if particles can grow in circumbinary disk or circumstellar disk in binaries or not. But on the other side, we know, as I showed you, that we can form substructure, that we can break disks and make them precess. So this perhaps leads to formation, that we can stop the drift of material. Then we have misalignment, which naturally arise from these configurations. We can also slow down viscous evolution in some configurations. And there is a thermal processing of dust that could be connected to what happened in the solar system before. And the tricky part is that there are several timescales to consider here. And so you have the orbital timescale, so the period of the binary, the viscous timescale, but also the secular one, which is sort of the order of 100 or 1,000 binary period. So that's the tricky part. And that needs a dedicated methodology, and I think Phantom is doing very well in dealing with these multiple stellar systems. And the ultimate goal would be to have a very robust statistical approach of what could happen for any multiple stellar system with disks. And when it comes to flybys, there are basically 3 categories. We have these non-penetrating, grazing encounters, and penetrating. So these ones are the ones that were discussed by Eli before. This is the one, UX Tauri, the one I just showed. And there are some hints that sometimes flybys occur really far away, but they still do something to the disk. But basically, the 5 reasons you should care about stellar flybys is that the environmental effects really matter in star formation, so when the disks form. Then that could lead also to accelerated dust growth or even fragmentation growth changes in the disk. That can also lead naturally to misaligned planetary architectures, which is something which is emerging from surveys. And there is dynamical instability and ejection that, again, naturally occurs in these disks that can be connected to the roaming planet population. And perhaps there was a stellar flyby in the solar system. That's something that's being debated at the moment. And just the last point I want to mention before I end is that what do we know about planets in multiple stellar systems? So basically here I'm showing just for binaries what we know. This is a bit old now, but numbers, this is the trend basically. So you have basically 2 types of planets. You can have planets around one of the stars, or you can have a planet which is orbiting the center of mass of the binary. And here you have different detection techniques. Basically here you have the S-type planets, the ones around one of the stars, and here you have the circumbinary planets. And you see that there are very few of them. So this is a bit worrying, because if I'm saying that it's important for planet formation, but in the end I tell you that there are very few of them, there is a problem there. But actually there is a very strong observational constraint against, observational bias against circumbinary planets. Because these stars are problematic, so they're put aside, and we're not seeing what's happening here. And we only have a few examples. But last week or 2 weeks ago, there was this very nice discovery, which was the first exoplanet discovered with radial velocity alone. So this is very exciting, because it means that now from the ground, we're able to catch circumbinary planets. We don't need to go to space. And basically what they detected is this planet C in this system, thanks to this survey called BBOP. And well, you have here the parameters they derived. But this is exciting also because this is the second multiplanetary circumbinary system discovered. So we're starting to see several planets in around the same star. So here you have the binary and you have 2 planets. And here's where there is a problem at the moment. We know that there are 750 planets in binary systems, but only 75 are P-type planets, so 10% of them. And if you compare that to the overall population of exoplanets, that means that there are only of the order of 2% of all the exoplanets known are P-type planets. So you can say, oh, this is marginal, this is ridiculous. But actually, as I said, there is a very strong bias against these planets. So I think we're only seeing the tip of the iceberg, and this population will emerge in the next years, and we need to understand how to connect this with disk dynamics. So now, coming to the conclusion, I hope I convince you that young stars with disks are very likely part of multiple stellar systems, and there is an emerging population of disks that we can model with Phantom, and we can derive some conclusions about what would happen in the systems. Binary and triple stellar systems, thanks to this comparison between hydrodynamical models and observations, we can now connect orbital elements to disk morphology, I would say, in a robust way. And there are multiple stellar multiplicity signposts in disks. I showed you there are spirals, shadows, warps, rings, gaps. There are many things that can happen. And this is very exciting because we are working closely with observers. And we need to understand what's the impact on planet formation. And I think multiple stellar systems are kind of simple, but yet very complex. But they still form very efficiently planets, I guess. So we need to understand what happens. And the avenues ahead, I think, is that we have this dust dynamics in multiple stellar system, and we need to understand what happens to tiny dust particles, how they can grow, if they're chemically different, where would you trap the solids, and where you would form the first planetesimals. This is an open question. We don't know yet. And we can also start to search for multiples with disks and planets, and as I told you, there is a population emerging from there, and we need to draw some statistically robust conclusions on that. So we need to understand what to search for. And last, there are these planetary architectures in multiples. And since there is a broader variety of mean-motion resonances in multiple stellar systems, there are things which are drastically different. So what would happen of things that would happen in a single stellar system as in the solar system. And this, again, is a kind of an open question. Many people are working on this. But where I think we can do something is to try to connect what we expect to happen in the disk phase to what we will be observed for the planetary architecture. And with this, I conclude. Thank you very much.
If you look at our solar system, can you predict if it was produced by a flyby?
So if we look at our own solar system, I mean,
Been here for 4 billion years or so.
yeah, I think there are hints of that in the trans-Neptunian objects. If you look at the distribution of trans-Neptunian objects, you see that there are some alignment of the orbits, which might indicate, so there is this idea of planet 9, but it is also this idea that there was a previous encounter in the past that misaligned part of the solar system. There is also the 7-degree misalignment between the ecliptic plane and the rotation axis of the star. This is something that happens as well with flybys. And the last piece of evidence, which is a bit under debate, I think it's not settled yet, is why do we find all these calcium and aluminium-rich inclusions all over the place in the solar system? Is this related to an encounter that happened to hit the disk in such a way that you melt everything and then you cool down again and form all these CIs? Those are evidence that are out there. I wouldn't say there is a robust way to say, yes, a stellar flyby happened.
So you could predict how many systems like our solar system exist?
That's a hard question. How many? I can say...
We know so much about them. It's a question of how they evolve, I suppose, over 4 billion years.
Well, we're not modeling for sure what happens at 4 million years, on the 4 billion years, but
yes,
we know that there are specific events that can explain why solids seem to have the same composition very far away from the star, where presumably they didn't experience such high temperatures. Flybys are a natural solution for them. It's a bit hard when it comes to quantify what's the fraction of stars that that had an encounter.
It's not a bit hard, it's very difficult.
Yes. But we think that perhaps half of the stars encounter another star during the disk evolution phase at a distance of at least 1,000 AU, at most 1,000. So if you take that sphere and then you compute what's the probability of having an encounter with another star, probably during the first 3 million years, the ratio is of the order of, could be around 50%, which means that stellar flybys are relevant for disk evolution.
It's difficult to say it's 50% because you don't know what the probability distributions are.
Yeah, it's a complicated question. You need to understand the dispersion, the initial distribution of stars, the dispersion, velocity. It's a complete other topic, but a decent fraction of systems encounter another star.
All right. Any other questions? I've got one that's maybe, I don't know, I probably just don't know. What are P-planets?
P-type planets? Oh, sorry. So P-type planets are the ones that are orbiting around the center of mass of the two stars. So it's what we call a circumbinary planet, if you wish. It's like Tatooine in the Star Wars. That's a P-type planet. And S-types are satellite planet, if you want, orbiting around one of the stars. And the interesting thing here is that you can put some limits on the stability of those planets, and you happen to see those which are stable, of course, for obvious reasons. But I think this plot here will be much more populated in the next years. And something I did not mention is that many of these systems seems to be misaligned with respect to the orbital plane of the binary. And this is something really interesting because that's hard to explain if you only have single stars, but when you have several stars, misalignment is completely natural.